Thank you. And I will speak today about statistics of accreting sources, and instead of describing individual sources, which you already heard a bit, I will speak about statistics, and I will try to explain you why statistics of sources is important thing to study. For example, I can say the following thing, that statistical study of accreting sources or just different sources in astrophysics can help you to understand the following thing. It can hint on the origin of astrophysical phenomena if you do not know it, or you can even determine the origin from statistical study. You can determine evolution of astrophysical objects, which usually, typically, you cannot do by study of individual objects. Or you can determine the importance of their contribution to another astrophysical phenomena. For example, you can determine the contribution of some number of objects to the total emission of galaxies and so on. And I'm pretty sure that you know statistics can give you an important answer. And for example, these conclusions was definitely extracted from statistical study of this phenomenon. Okay, let's go to galactic and extragalactic astrophysical sources. Broadly, it can be, at least for high-energy astrophysics, broadly these sources can be separated into several classes: high-mass X-ray binaries, low-mass X-ray binaries, and cataclysmic variables. And among extragalactic sources, I will talk about AGN. Statistics of galactic sources started virtually from Uhuru satellite. And already first sky surveys demonstrated several important findings. That first of all, you see a lot of X-ray sources along the galactic plane, and a lot of high-mass X-ray binaries, or majority of them, was distributed very closely along, close to the galactic plane, and a lot of low-mass X-ray binaries was discovered in galactic bulge and throughout the whole galaxy. One of the latest and most deep surveys of the galaxy, at least with respect to these galactic binaries, is the Integral all-sky survey. In particular, Integral spent a lot of time observing galactic plane and discovered a lot of sources which were not previously known due to its particular properties. One of the sources, and maybe typical or archetypical for this new integral sources, is this one. And this source was discovered, it was the first source was discovered with integral, and its strangeness comes from the fact that majority of its flux come in hard X-ray, not in soft X-rays. If you look at the spectrum, you see that it's virtually disappear from the view if you look at energies where typical surveys were done in with ASCA or ROSAT or XMM or Chandra. So you see that source is very bright only in hard X-rays. And a study of the source showed that it is high-mass binary with optical companion, which have a very powerful wind, and this powerful wind just engulfs the X-ray source and absorbs a lot of X-ray light from the source. And studying in infrared, for example, you can see here broadband spectrum of the source in infrared, and you see a lot of emission from dust around the source. So it definitely shows that the source is enshrouded by dense stellar wind. Study of integral of galactic plane with integral demonstrated that the number of such sources is high. And for example, here I can show only small part of the sky directed towards one of the tangents to the spiral lamps, and you see that all these sources which are marked with arrows, they are high-mass X-ray binaries. And if you look at regions away of these tangents to the spiral lamps, for example here, this is distribution of number of sources along the galactic plane, and positions of spiral lamps are marked by these letters. And you see that high-mass X-ray binaries, which are green or which are blue histogram, they are very concentrated to this position of spiral lamps. And you see that the low-mass X-ray binaries, which are here in red, is definitely do not show this concentration. So we can easily derive from this that high mass X-ray binaries are located in the regions of young stellar objects, where we have a lot of young stars, and only here these high mass X-ray binaries can survive and can be seen in X-rays. And this is another representation of the same graph. So you see here in 1D plot, and here it's how it looks like in the sky. So we are sitting here, and this is spiral arms, and gray shaded area is just showing the number. The darker the sector, the more high mass X-ray binaries you see. And this is compatible with what we expect in the case of spiral arms structure in our galaxy. Another interesting thing which can be studied with these surveys is, of course, low mass X-ray binaries. We already told about that. And what very interesting thing we can expect from deep surveys. For example, one of the phenomena which we might observe is the transition of so-called magnetic stellar wind breaking to gravitational stellar wind breaking in low mass X-ray binaries. I briefly describe what it means. Usually, people are discussing magnetic stellar wind breaking as a mechanism to keep Roche lobe in contact with the size of the star. So the idea is that if you are in low mass X-ray binary and you lose mass from smaller mass companion to neutron star, then the size of the Roche lobe increase somehow, and you just stop accreting at this point. In order to keep accretion, you should break your system. You should diminish the angular momentum. And in order to do this, you should have some mechanism to remove this angular momentum. And it's considered that if the stellar mass of a normal companion star is high, then the magnetic wind can remove angular momentum from the system. And at some point, this mechanism stops, and if you have mass smaller than something, then probably it's anticipated that gravitational wind breaking appears. And it is demonstrated here is very long ago proposed theory from paper of Herbert and Swan in 1981. Then you see how evolution of m dot with time of some mass, some low mass X-ray binary. So effectivity of magnetic stellar wind breaking is diminishing, and gravitational wave removal of angular momentum is increasing. And at some point there should be just change from one mechanism to another. And in relatively recent paper, it was proposed that the sign of these mechanisms can be seen from the shape of luminosity function of low mass X-ray binaries. The idea is simple, that if you have low mass X-ray binary which lives for a giga-year or so, it means that a significant amount of mass of optical companion was consumed during this evolution. It means that the currently observed luminosity function, which depends on the mass of the optical star, depends on what mechanism drives your accretion. And it was shown in this paper that if you have luminosities higher than some value, approximately 10 to the 37 max per second, magnetic wind breaking gives you approximately this slope, and gravitational waves breaking give you this slope. And this prediction can be checked with presently available data. Another important point which can be studied with study of luminosity function or with surveys, that there should be some propeller regime operating in low mass X-ray binaries. The idea is again very simple, that if you have a neutron star with some finite but non-zero magnetic field, then if your accretion rate is smaller than something, then magnetic field pressure is higher than accretion, than run pressure of the accreting flow, and it means that accretion should abruptly drop. And this mechanism was observed in transients. For example, here I show the example of Aquila X1, when you see that some gradual decrease in luminosity in X-ray was changed by abrupt drop, almost more than 2 orders of magnitude within a day. and it was interpreted as a demonstration of this propeller regime. And you can deduce what is the magnetic field of the Newton star in this case. If you go and look at the luminosity function, then you can deduce what is the average for the galaxy, for example, magnetic field of the Newton star. Because here you can only see in transients, maybe there is some bias effects, but in the luminosity function all biases should be removed. Okay, and I was talking about that this can be done with surveys, and this is a survey of integral of the intergalactic bulge. Here you can see the shape, approximate region of the galactic bulge, and this is image from deep integral observation of this region. You can probably hear some chauvinistic claims from Chandra and XMM people that they can do anything better. But actually it's not so, at least in this case, because if you see what is the Chandra field of view, and if you can multiply the number of observations that they can do in this area, and multiply the number of kiloseconds they can spend, it would take them 30 years or 100 years to make the same deep observation of the galactic bulge as integral can do. For example, I can show you this image, and this is image of 3 megaseconds of XMM. I completely throw out anything that is close to galactic center, where they spend a lot of time. But this is 3 megaseconds. You can compare what you can see in integral. Or this is a Rosette. Of course, it covers the whole sky, but the sensitivity of Rosette is much worse in this area. It's even not remembering the fact that some sources can be absorbed, as I showed before. Rosette in this area is maybe 10 times worse than integral. So I will skip this point. And okay, what we actually see, we see with integral this fact that the slope that was predicted from observation of distant elliptical galaxies and from theoretical point of view about magnetic stellar wind doesn't continue to what low luminosity. It definitely has a break at around this luminosity, and in this area probably mechanism of removal of angular momentum is different from what we have here. And here we definitely know counterparts of systems, and we know that they are not gravitational wave emitters. And now we should do a study in this area. And this area study is much worse, much harder from the point of view of observations. Because these sources are faint, and even they are not only faint, but they are small from the point of view of geometrically small, and that means that in optical they are very faint. It is anticipated they can be as faint as absolute magnitude -5, -6, or even theta, and in this case you need very accurate astrometric position in order to discriminate between some foreground or background stars and your real system. And we selected sources from the galactic bulge survey. Here all low mass X-ray binaries or suspected low mass X-ray binaries marked with this red circle, and we have a special Chandra program to identify these objects, and we have accurate astrometric position, and afterwards we will try to initiate very deep observation of the galactic bulge region in optics and hopefully in infrared. Okay, another aspect that we can subtract from or extract from all-sky survey of integral, for example, is the study of faint emitting X-ray systems like cataclysmic variables. Cataclysmic variables are faint. It means that we will not see them at the galactic center distance, and again it means that they should be distributed along the whole sky. It again cannot be repeated with XMM or Chandra. The whole sky should be covered in order to extract reasonable statistics of local CVs. And we have done this, and we constructed luminosity function of CVs with integral, black points, and with RXTE, red points. And we obtained that we have estimated some numbers, and also we can estimate the cumulative emissivity of these CVs in this high energy band. And I don't know, have you heard about the galactic rich X-ray emission or not? I will tell you in 2 minutes that if you subtract the flux from all sources along the galactic plane that you can easily see as low mass X-ray binaries, you will see something like a pale stripe along the galactic plane, and this pale stripe was long considered to be diffuse emission of the galaxy, but there was a big problems interpreting this emission. But now we can see that actually cumulative emission of CVs, which we can measure in X-rays, now this cumulative emission X per second per solar mass of the stellar population, if we recalculate this value into the galaxy, we can easily explain the shape and the spectrum and the normalization of galactic rich X-ray emission. And also we have measured with CVs, we have measured the distribution across the galactic plane, which is also compatible with what we can expect from stellar evolution. And this is just maybe some pretty picture how luminosity function looks in hard X-rays. And you can see that the contribution of low mass X-ray binaries and hard X-rays and CVs are already quite compatible with each other, which is very important, because a lot of people who are doing studies in Chandra band and Rosette band think that if you subtract low mass X-ray binaries, then nothing in galaxy will remain. And in reality, it's not so. There are a lot of contribution in CVs. But this is of course true in particular in hard X-rays and soft X-rays a bit different. Okay, I will skip this point. I have time. I can maybe not skip. Another important issue about this galactic rich emission, that we can not only determine the flux in the galactic plane and compare with the flux we can predict from local population, but we can measure the shape. And the shape of this galactic rich X-ray emission can be again explained by contribution of cataclysmic variables. And why cataclysmic variables have this particular shape, this cutoff of energy at this cutoff at this energy? And this is again can be very easily explained, because temperature of the plasma, which you can reach in the cataclysmic variables, it's accreting white dwarfs. The temperature of the plasma is not higher than temperature, virial temperature of protons around near the white dwarf. And the temperature, virial temperature of protons at the surface of the white dwarf is about 10 or 20 keV. This is exactly where we see this cutoff. So we do not, if we would see something that is power law going to infinity, that would definitely contradict our theory. Okay, integral also was used several times in study statistics of local universe, and in particular statistics of AGNs in the local universe. One of the immediate things that you can extract from the whole sky, and you see that this is an image of the whole sky with integral, and here we have almost 100 or a bit more than 100 AGNs. And from this number of AGNs we construct a luminosity function. We can compare this luminosity function with those measured at distant redshifts. For example, our luminosity function obtained with RXT integral in local universe, and then is further and further, and we see definite evolution of population of AGNs. Then we studied energy spectrum of AGNs, and we did it in several ways. One way is very simple, and just to stack all sources in some flux bins in order to not to introduce any additional noise, and we just simply stacked sources which has more sigma in detections, which have more photons in our sample, less and less photons. And we see that in all sample there are at least hint on high energy cutoff in the spectrum. And then we have done another example. We averaged in a clever way, let's say this. In a clever way that we estimated the luminosity density. So what would be the spectrum of the square or cubic megaparsec in our local universe if we sum up all AGNs? And in this case we obtained this spectra. This is spectra for low luminosity AGNs, and this is for high luminosity AGNs. And if we now sum them up, integrating of the whole universe, taking into account evolution of the density of AGNs, Now I will just briefly describe this. If you have any question, I can return to these images. Then we can compare this cumulative emission of all AGNs in old universe to the to CXB, to the cosmic X-ray background. And this is points of cosmic X-ray background measured with integral again, for example. And this is the shape of the spectra we can predict convolving all our assumption and convolving our measured spectrum of AGN. And we see that it's pretty compatible with measured CXB shape. And you see on these different plots, here density of AGNs, emissivity of AGNs was assumed to be constant at high redshifts, and here it was declining. So that there is a bit discrepancy in normalization, but taking into account our simple model, that is not one that can be. Okay, then another interesting thing that we can do with sample of AGNs, which we see with integral, is to study and to check AGN unification models. AGN unification model assumes that you essentially have the same spectrum of central agent, but you observe different shape of AGNs just because of the different viewing angle. But in order to test this model, you definitely should have a large sample without any biases, and integral presents you this sample. So we just started to do this, and for example, we already discovered some interesting things, that O3 line, that is usually considered by optical people as a very good tracer of AGN accretion rate or AGN intrinsic luminosity, not always very nicely follows the hard X-ray luminosity, because probably of different reasons. One of the reasons can be that this AGN is just seen by in H1. So, for example, in this case, we can expect that intrinsic luminosity in optics, in optical line in particular, in this one, can be absorbed just by dust laying in the galaxy. But possibly it can be some another reason. But we only started these studies. Another interesting thing that can be, and important, I would say, that can be obtained from the AGN sample of the local universe as a local large-scale structure. And briefly, it's the following thing, that we definitely know that in a local universe within a couple of 100 megaparsecs, universe is not uniform. It definitely has concentrations and voids. For example, from IRIS sky survey, it was constructed a density 3D density map of galaxies in a nearby universe. Here is a cubic volume about 200 megaparsecs across, and you see that there are different concentration of galaxies in our local universe. And for, the largest anisotropy which you can see in the sky is approximately directed in this, directed along this axis. And with integral all sky survey, you see this already with the available sample. If you divide your sky in two parts, one part is directed this way, another part is directed this way, and you construct log n log s distribution in these directions, you easily see this difference. And this difference 11 to 1 is a probability that would be from a random distribution with the same anisotropy is less than 3.5 or something sigma, or almost 4 sigma. And we are actually not surprised to see this, because we definitely know that in the local universe there is anisotropy, and we see it in IRIS, and now we can see this in 2-mass galaxy survey. And if we construct a similar plot with integral AGN sample, we see this color map. This color map shows the density anisotropy. Okay, I'm very close. Density anisotropy, and the contours are density anisotropy from IRIS infrared galaxy survey. So we see the similarity is very high. Another, I would say, unique thing that can be extracted from the anisotropy on the sky, and you cannot extract the same information from anything else, is anisotropy in the total CXB surface brightness. What I mean by this, so if you look at the sky, this for example, CXB surface brightness, look at the sky, CXB is very uniform. It's within a couple of percent or 3%. It means that if you look at different directions, the intensity of the CXB is almost the same. But it's not absolutely the same. And the shape, the pattern of not the sameness of the CXB on the sky is actually recorded by the shape of density of galaxies in nearby universe. Because if you consider very far universe, then it will be absolutely the same, within less than a percent. And nearby universe, which has a very large density gradients, then you will see some pattern on the sky. And simulations or study with real iris galaxies, for example, here, you see that mean anisotropy, which you can see on the sky, it's accumulated over the first 100 megaparsec. And if you look at further universe, then anisotropy is very small. And we studied this, so essentially it can be seen that we can feel what is the pattern on the sky and read information about emissivity in the local universe. And we did this analysis with RxTE, and we extracted the following information, that every X-ray emitting thing, that how faint it would be, it doesn't matter for our analysis. Every X-ray emitting thing is recorded with this analysis. And we say that that emissivity in X-ray of every source in the local universe, which is fainter than 10 to the 42, for example, x per second, has this value. So it cannot be higher than this. And this value is compatible with what we know already for normal AGNs. And we see that there is nothing much left for something unknown. For example, somebody can say that if you have very faint source, you can dump millions of them in the local universe, and you will not see them because they are too faint for you. But it's not possible, because in this case you will record these sources into the pattern on the sky, which we will see in this analysis. Okay, and I'm already for summary. HMXBs are discovered in the spiral tangents, and now this result is very well pronounced with integral observations. Faint Lomas X-ray binaries might be gravitational wave emitters, and this should be studied with optical and RxT combined observation. Very interesting thing. Population of CV is measured almost for the first time, because it's very complicated to construct unbiased sample of CVs near the sun. Luminosity function of AGNs is obtained from integral all-sky survey. Absorption distribute, so I'll skip this point because I haven't described it. Local anisotropy of AGNs is detected, and the emissivity of local universe is measured. Accuracy is not perfect right now, but it can be in principle improved, but at least it's definitely shown that not a lot of emissivity left for faint low luminosity AGNs or for even fainter sources in galaxies. So,
Thank you. Questions?
When you measure cosmic X-ray background and you want to measure anisotropies, you associate those anisotropies with the density of AGNs, right?
no, density of galaxies.
Density of galaxies. So they are
You mean this
dominated.
one or previous one?
Anyway, so when you're talking about anisotropy of
No, I was talking about two
X-ray
things.
background.
This thing is anisotropy of the total emission, and that it was anisotropy of the density. This is anisotropy of
emission. Is it dominated by what? By normal galaxies?
No, it can be dominated. It's probably dominated by low luminosity AGNs. But of course, we made assumption. Assumption is the following: that X-ray emitters proportional to density of matter.
Yes, that was my question. If you have a more like dense environment, do you expect maybe there will be more AGNs there and you will get more X-ray emission? So it will be not directly proportional to the density, but maybe some power of density.
That is the question, but this question partially can be answered by the previous study. And with this study, at least within AGNs which we studied in this example is very powerful AGNs. They are not numerous within I don't know, a couple of galaxies or within clusters of galaxies. It means that distance between these AGNs at this luminosity is very high. And here we show that the proportionality is almost 1. So 1 to 1.
Mhm.
There is not a power. It's not a second power, third power. It's 1 to 1. And with faint, it's possible that it can be not the first power, but it also be recorded in a density in contrast. You can do this, but it will be even further. You will see this even more pronounced. For example, C is 1, a factor of 1, T is factor of 10. But you will see this. It will be even tighter up already.
More questions?
Your characteristic variables, the magnetic ones you fitted there, have you compared the counts with the known counts in number counts in the near universe, the nearby ones?
Yeah, this is nearby ones. This is nearby. That's like 1 kiloparsec away at most. But maybe you meant
from before.
From optical.
Yeah.
It's very tricky question. Tricky from the point of view that if you say what is optical, you do not know how it translates into X-rays, because luminosity between optical X-rays is not very well understood. But broadly speaking, yes, it's compatible. But if you go into details, this is observed point, unbiased. And in optics, it's very hard to estimate statistically because it's very biased towards different things.
It's a little bit motivation for my question as well. I mean, one of the things that one can look at. So
yeah, I would say that if we look at the very luminous, which are more easy to identify and quantify from optics, it is more or less compatible. This is like short answer, but for long answer we can discuss this later. That is an interesting question, and we will always motivate people from optical that it is very important to compare unbiased way, and it's very hard actually to invent something unbiased way in optical band, because here our density of our sources on the sky is very small. It's very easy to say it is at AGN, for example, or CV, and there is no much more sources. But if you look in optical and just you would like to cover half of the sky, then it's very hard for you to extract information what is CV and what is this density and how strong you are biased towards detection.
many of the nearby ones also discovered by X-rays before, like the Rosat.
They are strongly biased. No. With Rosat, they are strongly biased because, for example, these CVs, which are very luminous, they are very strongly absorbed at the same point because there is a lot of matter that is flowing towards the polar caps, and it's going through X-rays going through them, and you absorb. And with Rosat, it is very well known that magnetic CVs are strongly biased in the Rosat sample. In hard X-ray, it's completely not so.
More questions? Okay, well, let's thank the speaker. The next talk is by Diana Hannekainen on relativistic jets in recent results from multi-wavelength observations of microquasars.
Everybody. The topic that I was sort of asked to give a brief talk about was in fact recent results from multi-wavelength observations of microquasars, but I would rather change the recent results from into sort of a brief glimpse of. I'm just going to touch very briefly on three sources. Two of them we've had some dedicated multi-wavelength campaigns on recently, and one source has been talked about a lot this afternoon, and I'm just showing one snapshot of that. And Stéphane Corvelle already this morning gave us a very comprehensive view of microquasars, so I'm not going to dwell on them very much. I just put this picture up here just to remind you all, in case you've forgotten between this morning and during the lunch break, microquasars basically compact objects accreting matter from a donor, Roche-Loeb-filling donor star, in the case low mass binaries, X-ray binaries, and wind from high mass X-ray binaries, and these exhibit jets. So this is just a small collage of the sort of outbursts that we see in light curves from a selection of X-ray binaries. In the top left-hand corner we have XTJ 1550 minus 564, and we see a whole series. The purple line here is the Batsy hard X-rays. This is a source that started its outburst in the hard X-rays. During that, there was a rise in the soft X-rays, and then there's a flare here that occurs at all wavelengths, from the hard X-rays down to the radio, and jets were actually imaged at the time of this outburst. In the bottom left-hand corner, we have GRS 1915 plus 105 that was also discussed briefly. This is a very long-term light curve here. This is about 2 or 3 years, I think. And the top panel is soft X-rays from ASM, bottom panel is radio from the RILE, and basically this is a source that does not show any sort of clear outbursting, but it is flaring. There's chaotic variability the whole time at both these wavelengths. Cygnus X3 I shall talk about a little bit later on. Sig X3 we also see complicated relationships between the radio here in the red, the hard X-rays in the blue, and then Stefan talked extensively about this source GX339-4 this morning, where you can see very clearly the state changes. This top panel is the radio, the middle panel is the hard X-rays, and the bottom panel is the soft X-rays. And the reason that we observe these sources at all these, oh, yeah, I have this to work with. The reason we observe all these sources at all these wavelengths is so that we can try to come to a comprehensive picture of the different emitting regions in them. And just very briefly, Stefan did already talk about this, but very briefly, the very simple picture that we have for X-ray binaries is you have the X-ray spectrum here, you have when they are in the high soft state, you have the spectrum dominated by the disk component, and then in the hard state you have a spectrum peaking at about 100 keV in what was historically called the low hard state. There's a whole bunch, there's at least 2 new nomenclature schemes, but just for historical purposes, I would just stick to these 2 for now. And Stefan also mentioned very quickly that in the high soft state you have the accretion disk extending down to the last stable orbit around the compact object. And in the hard state, then you might have, this is still a big question that I will get to at the end, you might have a sort of truncated disk and then a hot accretion flow here in the middle, and in the low hard state, as Stefan mentioned. Very importantly, you often have these compact jets. The less simple picture is that it would be nice if they were just high soft and low hard, but there are also several intermediate states and various other combinations where there's various combinations of the extent of the accretion disk and the amount of hot flow here in the middle. But I don't need to keep doing this. I just gave a talk 4 days ago where this thing didn't work. So, and Stefan also shows that these X-ray binaries with radio jets, when they go into outburst, they sort of follow a pattern. Many of them follow, not all. Definitely not all, and I'm going to show you a little bit about that later. But they sort of follow a pattern from the low hard state, or quiescent, where they go through the outburst, and in the transition from the hard state across to the sort of softer states. That's when we might see these explosive ejection events rather than the compact jet here. Now, one source I'd like to talk to you about is XTJ 1818-245. I wanted to stress at the beginning that this is all work I've done with various collaborators. I obviously have lots of collaborators at, for example, CEA at Saclay. I have collaborators at ESAC in Madrid and so on. But I just didn't put them on the front slide because this was something I cobbled together just yesterday afternoon. So, but this is work done by Marion Cadorel primarily, and this is a classic example of a X-ray nova outburst where you have the source is off basically, and then in the soft X-rays, then which is this red curve here, which is the ASM curve, there's suddenly it goes into an outburst, and then there's this decay. Now the vertical lines here delineate some integral revolutions, and we triggered some TOO observations during 3 of the integral revolutions, and the rest of the integral data is from public galactic bulge monitoring. And we also, Marion was very good at coordinating then, coordinating multi-wavelength, then also for the radio, radio with the VLA, and then some infrared at the knot, and then Swift, of course, is. Right, so this is a zoom of the start of the outburst here. Well, actually, we're at the peak already. And basically, there were two radio flares that were observed during this outburst. The first peak here was detected at 4.9 gigahertz, and the second peak some days later was detected at 1.4 gigahertz. And so here we just have the light curves, the PCA sort of harder X-ray light curve, and then the infrared down here. And the source basically it was in some sort of intermediate state. Here is a sort of a soft intermediate state. It went into the high soft state and then went back into the soft intermediate state. And basically, okay, we didn't quite get the start of the outburst, but if we plot the data points on the hardness intensity diagram, just like for that Q diagram that I showed a couple of slides back, like I said, we did miss the start of the outburst, but then we see some slight deviations from the classical path. The source actually did this sort of Z shape here. It transited a few times left to right here, and then it went back up left to right, and then it followed through to the end of the outburst. So that didn't quite follow, let's say it was close, but didn't quite follow the standard path. And these show where the radio flares occurred. And just to finish off on very interesting, that should be a gamma up there. These are the XTE and integral spectra. This is from the first integral TOO, and this is from the second integral TOO after the source had transited from the soft intermediate state to the high soft state. And then here what we did was we just plotted various spectral parameters. We just fit initially just a very simple model of a multicolored disk and a power law, including Gaussian component, and basically we see that this was the power law photon index here, which stayed pretty steady throughout the outburst, even as the disk throughout the outburst, even as the disk radius was sort of maybe increasing throughout. But this is just a very, very simple sort of modeling here. And just to wrap it up, XT J1818, we just put all the data together in one broadband spectrum. We don't have enough data to do any conclusive broadband spectral modeling here. But, and this, by the way, is not a fit. This is just a power law through the points here, just to show that there is an optical excess here. The optical is probably from the accretion disk and the companion star. But basically, if one just does very, very sort of simple modeling, we find that we need three contributions to describe the spectrum as one would expect: jet, a disk, and a hot medium. And the radio, which is shown here in these three panels, that's the 1.4 gigahertz, 4.8, and 8.4 gigahertz. There is some radio 5 days after the transition to the high soft state. It cannot be due to the residuals of the flare, so we think it might be ejected matter interacting with the ISM, as Stefan had suggested some years back. Now, SIGX1 has already been talked a lot about today, and this is not work that I have necessarily been totally involved in. And Stefan also spoke about the magic detection of SIGX1, so I thought that I would just complete the picture a little bit by showing you more of the integral spectra from this event. So this is the light curve, and let's see, we have this is in Crab here. So we have the light curve here, and as Stefan said, it wasn't exactly an outburst as such. But there is the source did brighten significantly during this event, and the red arrow shows where the magic event occurred. And this was the first observation of a persistent black hole binary in a stable hard state at such levels of intensity over basically such a long time. And these are again the light curves, and the magic observations happened here. And you might have all seen this morning. I regret I was not here for Robert Wagner's talk, but The point is not so much to go into this as to show that one can do a very nice spectrum that goes from a couple of keV all the way up to the TeV magic energies. And this single power law from the MeV to the TeV is probably not likely, but I believe this is still being worked on. I'm sure that somebody here knows about more results. And quickly, the integral spectrum is depicted here. And this is the typical hard state spectrum of SIGX1. So for comparison, here this blue spectrum is from the outburst, and the red spectrum is the average over the whole revolution. And basically the source was about twice a factor of 2 brighter than it has been in the past, and it sustained it for quite a long time. And it stayed in this bright state for several days. Let's say the outburst lasted for about 10 hours. And now to conclude, I would like to show a few of the last things that we're working on. And it's Cygnus X3, and I know that in this room there are several people who have worked extensively with SIG-X3 and know a lot more than I do, but I would like to just show a little bit of the latest work that we've been doing. This is again the SIG-X3 light curve reproduced here. With blue is the hard X-rays, red is the soft X-rays. It is, just to remind you, it's a Wolf-Rayet star with a compact primary. The compact primary might be a black hole, probably a black hole. Neutron star is not yet ruled out. It has an orbital period of 4.8 hours. So Cygnus X3 is very interesting because it has the companion of the order of the high mass X-ray binary, but the orbital period of the order of a low mass X-ray binary. It's a very strong radio source. Some of the strongest flares have been measured at about 20 Janskys. Definitely the strongest galactic X-ray binary radio flare. And there's a very complex relationship between the radio and the X-rays, as we will see. And this it exhibits orbital modulation in the soft and hard X-rays. And this is a collection of all the spectra as at the time collected. This is about a year ago, just over a year ago. All the RXTE spectra of SIG-X3, where you can see the soft state spectra and the harder state spectra. And SIG-X3 is very interesting because it exhibits all of the states of X-ray binaries, from the hard to the intermediate. There's the very high, there's the ultra soft. The interesting thing to note with SIG-X3 is that most X-ray binaries in their hard state peak at around 100 keV, and SIG-X3 peaks much lower at about 20-30 keV. And as I mentioned already, it exhibits a very complicated relationship between the soft and the hard X-rays. There are some hard X-ray between the X-rays and the radio. There are some radio flares, some X-ray flares that exhibit radio, some that don't. And Linnea here already, she studied this last year, a year ago. And you can, if you plot the soft X-rays here and the radio here, you can see that for a wide range of X-ray luminosity, the radio stays quite steady, and then something happens around here, and then the radio goes chaotic at this stage. I'm not going to go into this very much more, because I can't, because I've just been told I only have 2 minutes. But this is again the Q diagram of all the data points of SIG-X3. You would think that it looks like a Q diagram, but in fact it doesn't follow the pattern around this way, but it'll flare up and down here, or it'll flare up and down here, rather than going across the diagram that way. And this is a multi-wavelength campaign that was conducted in 2006. There's a whole suite of instruments here, from XTE to Integral, Swift, right down to the radio. And 2 distinct flares were observed here. There's a 3rd flare that we haven't plotted yet here, but the flares are basically, these are the soft X-ray flares, and the flares are basically similar in nature. And what we have done is we have looked at the time. These multi-wavelength observations were conducted a couple of hours after this flare, 2.5 days after this flare, and so on. And so we've ordered, because the nature of these flaring this flaring behavior here is similar, we have ordered these flares according to time from the peak of the flare. And we looked at, we did a quick study on using principal component analysis, which is basically you find the fewest components that are sufficient to explain the data. And we noticed, I won't go into this much, but that 86% of the variation occurs is due to a low energy component, which we could attribute to the disk, and 12% of the variation is attributable to the high energy component, which is probably like corona. And this is in fact correlating to the orbital modulation. We have here the first component plotted here according to observation. So this is right after the flare, this is much further after the flare, and we can see that the first component stays constant around a certain value, and the second component is also orbitally modulated, but it dampens as the flare evolves, and it also changes intensity here. And there's the radio down here, with which we don't see any obvious correlation. And just to finish off, a lot of people have already talked about open questions, and I think one of the big open questions is exactly what happens here in the center. Stefan also had that question mark here. What exactly goes on here during the hard state? It could be any one of these things for now, maybe more. And spin is also a very important thing. 9015, 6055 all exhibit maximal spin. The SIGX1, for example, only exhibits a spin of about 0.02, and so on. So that was just a very quick picture of a few multi-wavelength things. What I wanted to highlight was that with lots of different wavelengths, you can try to come up with a full picture, which we can't yet, obviously, because we still have a lot of theoretical work to do, which would be nice to see you do that. Thank you.
Do you have time for questions?
Is A referring to the black hole Kerr spin? Or what?
Yes.
So how do we know SIGX1's such low spin value?
I just heard about it last week. I think it's a fairly new result. That's, oh, I don't remember now. Yeah, but it was, if I really thought about it hard, I'll let you know. I do have it, yeah. I just have to, but I just heard about it last week.
How do you know anyhow what's the speed limit, even for large scales? How do you actually measure it?
How does one measure spin, Yuri?
From the spectrum of the accretion disk, but I think this is very strongly model dependent. I mean, those people who have ever measured, look at the spectrum of the accretion disk, which looks like a big bump, and try to fit some accretion disk model, and then it's become, I think, very questionable.
Magnus has
What?
something to
Yeah,
say.
you can, I mean, even use the iron line from your phase limiter, but also you can use timing. So there are many things you can timing. I mean, you have to identify the few goes with and see how they go. I mean, to identify, if you are saying there are models saying there's a accretion disk component in the spectrum, we can use timing, see how the timing component moves.
Yeah, it's not. It's not solid, but it's just something that is brought up, you know, in discussions.
You mentioned, or you showed the sequence X3 observation, and you mentioned that this is probably Bob-Raista. But I just would like to point out that although it looks like Bob-Raista, a lot of things look like Bob-Raistas. For example, some nuclei of planetary nebula, and you would not say it's a massive, it has been a very massive star. So it's a Wolf-Rayet phenomenon which you observe, and we really don't know whether or not this came from a very, very massive star in the binary evolution. Just wanted to point out.
Okay. Thank you. More questions?
Just for 1818,
Yeah.
1818, the first source, you see that we don't have a Q shape, but the rise was rather fast, so you...
The rise was fast. We didn't catch it. In
No,
fact,
we don't catch it.
no.
Yeah.
We say we don't catch it, but then at the end, there's just that little Z bit, the Z bit. But no. I think I mentioned that we don't catch the rise.
Yeah.
We didn't catch the rise. So I mean, it probably would.
Yeah.
But then just as it goes through the evolution, it just deviates slightly. Not much, but slightly.
Any more questions? Okay, let's thank the speaker again. And the final talk before the break is by Anatoly June on non-thermal MEV emission from galactic superluminal sources, present status and future perspective.
Good afternoon, everybody. Okay. And thanks a lot, organizer, for inviting me and for the good weather you provided for the couple of days at least. Hopefully it will extend. And the topic is non-thermal emission. And I don't know how this thing works, but I will try. Okay, this pointer. So basically, the only few sources which were observed with Compton Gamma Ray Observatory, and among those were of course famous superluminal objects like GRO 1655 and GRS 1915, and certainly a lot of observations were dedicated to the Cygnus X1, which was one of the brightest X-ray sources in the energy range of the instruments on board of the Compton Observatory. I will just reiterate maybe some of the well-known to you results and some of the situation with study of those superluminal objects with multi-wavelengths campaigns of different kind were just shown in the previous talk and the talk which was before the launch. And a lot of expectation, at least I do have for the future, because MEV region seems to me could provide very interesting information on this object. And one of the possible missions grips might give us very nice results in the future, which hopefully will come. So one of the first superluminal objects in our galaxy, which was suggested by Felix Mirabel, this was this famous object, Einstein, 1742, which shows very prominent jet-like features. And it was quite easily to believe that this sort of picture might take place in the binary systems which are harboring very heavy black hole. Compton, one of the instruments on board of the Compton Gamma Ray Observatory, was imaging instrument first of all and has some limited spectroscopical abilities, about 8% of energy resolution at 1 MeV. Of course it was a complicated instrument as it has to be, but I do want to remind that this was just first generation telescope working in this MEV range. And it was pretty successful, which was demonstrated, for example, by results on the Cygnus X1. This is a work mostly by Mark McConnell. Final publication took place in 2002, but the work was lasting for more than 10 years on this object. And one of the probably best known results, was this famous spectrum, which definitely has shown that MEV emission from this high mass X-ray binary, possibly also having some jet from the core of the object, do extend into MEV region almost to 10 MEV. They're just usual bunch of models which are quite sophisticated, containing a lot of parameters of sub-models, let's say sub-components, and these models were successfully fitted to the spectra which were shown by Cygnus X1 with the use of spectra collected by OSI, by some instruments on board of the BEPASAX, and also by Comtel and BATSI. So it seems everything quite all right and understandable for Cygnus X1. But now comes a story about the superluminal guys. And I will start with GRS 1915. And here are shown light curves of 3 objects which were studied extensively by Comptel team. And GRS 1915 discovered by watch on the August 15, 1902, and Castro Tirado, this co-authors published immediately IU circular. And the object seems to possess quite extreme parameters. So distance to the object about 11 kiloparsecs, mass function 9.3 solar masses, and the mass of the black hole about 10, from 10, let's say, to 20 solar masses. Interesting point about this object is that before discovery, it seems was already active during the May 6 to 20, according to the BATSI data. It was curious, and we have looked back and found more on this object. This is just to demonstrate that Comptel indeed detected this object. This is a map at the energies of 0.7 up to 7 MeV. This is a map showing another episode for the energies of 3 to 7 MeV from this object. And maybe more striking was the result that when we looked back in the time, we have found, analyzing BATSI data with the help also of the BATSI team, and aggregate data, that the source, the superluminal guy, was showing quite a few outbursts. 1 year already before the major outburst which led to its discovery. It is very strange. It also shows that this crosses, by the way, this is aggregate crosses, like this. And aggregate for energy range from 100 MeV to 300 MeV. And this is BATSI points from 20 to 100 kV. So obviously object was already active 1 year ago, before the discovery. It's curious. But this object do have orbital period, which is extreme, 800 hours. Can it be somehow connected? I don't know, but one can probably speculate about this possibility. These are spectra which are made for, for these observations, and the dates are shown here in the MJD, sometimes it truncated Julian dates, but anyway, here are shown just Comptel points and the aggregate points. And you see, so the one of the spectra has clear detection of not only by Comptel, but also by aggregate, with quite small error bar. So again, energy range from 100 to 300 MeV. So this shows that this object do not only have MeV non-thermal, but this is hundreds MeV non-thermal emission. And this particular spectra are shown for this episode. This small one, which just shows that the object is in low hard state, so it's not flared. The next episode immediately connected to this one. This is red arrows. This is for Comptel time interval, and the green one for aggregate. If you just add up BATSI data to the spectrum, you can see that the spectrum follows in the same power law slope up to the break point, which is quite low in the energy. It's about 30 or 40 keV, and then it steepens, going up. So maybe this is sort of the quantization spectrum adding up to the power law. Can be. Unfortunately, we do not have spectrum to the much lower energies, but those type of breaks are present in many spectra of this object. Well, this is already next episode again in the lower state, but there was some sort of sub-flaring activity. And the next one, this one, is this episode here. So this was sort of high emission state. Those light curves, this is all sky monitor from ROS-XE. And this is again, you see here, that's not so noticeable break, but it's possible still to make 2 feeds with a steep power law to the lower hard X-ray and the quite hard spectrum for harder X-rays and MeV region. The same basically conclusion was drawn also by the case and et al. who was reanalyzing data together with GPL people, James Lin, using the same occultation methods. I just want to remind you that we were also using occultation methodic to derive Batsi points, but it was done by Marshall people, so much more conservative. Now, this is just some illustration for radio and X-ray connection. And now I'm coming to the GRO 1655. It was observed already for the discovery flare period, and it was detected again. I do want to underline this point. This is also pretty heavy black hole, but it's completely different in appearance, this hard X-rays and MEV region from the GRS 1915. We never have seen here sort of breaks. This is almost straight power law from, let's say, 20 TeV up to 10 MeV at least. That's maybe some rise, which is shown at some other spectra as well. And this is another episode of activity of this source, which belongs to this period of time. And again, this is the same spectrum. It's the same slope, minus 2.6 about, power law, from 40 TeV up to again 10 MeV. And if you compare those two episodes, so the points of OC and Comptela put together here in this spectrum, OC has much more points, but I just decimated some of those just to make a more clear picture. And you see, the spectrum is basically again the same. So this is confirmation from at least 3 instruments that the spectrum of GRS 1655 has the same power law, from 10 TeV up to 10 MeV. I'll now just finish the story. I just would like to make a cautious note on this analysis with Batsi occultation methodics. Because the source is not particularly bright, you need to collect a lot of days. And while you are doing this, you are producing finally spectrum, which can be misleading because this is integration of about 100 maybe separate spectra. And then you just somehow make it sort of maybe not absolutely up to the flaring episode, which here you see have some time details. So this is one flaring episode, and this is already completely different. And when you zoom those up, you have this spectrum. So it may be not the complete story, to say the least. To sum up our results, I just want like to underline that COMTEL has detected MEV non-thermal emission from both superluminal sources. Curious that emission MEV and hard X-rays from GRO 1655 obviously did not change the slope for almost 2 years after the discovery. Of course, we were not covering all time interval of these 2 years, but whenever it was bright, it has shown the same spectrum. GRS 1915 has shown some kind of activity already 1 year before the discovery by hard X-ray telescope aboard of the Granat. And it shows this emission in both states, low hard and transition states. And the spectrum again can be consistent with a single power law from 100 TeV to well above 10 MeV, and below about roughly 100 TeV. We can see a break of the spectrum at energies of break position from 30 TeV up to 100 TeV. Of course, this is not the whole story, and we were shown this picture already today, which shows that environment of microquasars can be quite complicated, and this is this blown up image of the shell around Cygnus X1. And to add to this, I want just to mention that there's some nice data exist, X-ray, taken with high energy rating on board of the Chandra of analysis for GRO 1655, which clearly demonstrate that environment really complicated, very clumpy, and very dense. So the picture, theoretical, which was presented like this, so there's some companion stuff from which is goes accretion onto the object, is not complete. You have to take into account that here around a lot of matter, which is very clumpy, with very fine distribution, which we need to know before interpreting results of measurements. And we need definitely, of course, multi-wavelength observations, because you see the models for emission from microquasars are having quite interesting shape with a lot of ups and downs. And to cover all those, of course, you need to have instruments from, let's say, 100 electronvolts up to 100 teravolts. And MAV region is quite important, because to this region are coming some of the possible cutoffs, or maybe synchrotron emission, or just due to Comptonization, input, etc. And to do this properly, one need to fill in this gap, which is existed present after the Compton was operated. Because as I said at the beginning, MAV region is very rich for new information. And to cover this gap, emission like grips will be a very proper one, with its effective area exceeding 1,000 square centimeters, energy resolution, which is about 1% at 1 MeV, because basically what you need, and what was shown, demonstrated on the base of Compton gamma ray observatory, is that you need still at MeV energies all sky monitor type instrument to be flown. And that's what is possible to do with grips in 5 years mission. That's it. Thank you very much.
I have a small question about life curve of 1915 before discovery of granite. It looks strange to me because, can you please show me that?
I will try.
Yeah, this one.
Yeah.
It looked to me that error bars are definitely underestimated, because we see that a huge number of points exceeding 5 sigma in minus, 10 sigma to minus flux and so on.
Yeah.
So I would multiply these error bars by a factor of 3, and maybe all these other points would be not so important in this case.
Yeah, so maybe significance of this sort of flaring overestimated.
Or even detection.
Well, detection, I don't know. There are some still pretty
How
high points.
1915 is sitting in a
Look.
very dense environment.
Look,
How Batsy
look
can
to
be?
this point.
That's if it's systematic and can be as high as possible as you want. It's sitting in a very dense environment, and the Batsy cannot really resolve a lot of things. So I would not be surprised. And even if you take this flux is huge, as photons per centimeter per second. So 10 to the minus 2, even higher. So it means that if you extrapolate it into a soft band, it would be crab or so.
Crab, okay.
If
But
you say
I'm
2.6
not-
slope,
I'm
it's
not
crab, it will be visible with any kind of instrument.
I'm not so sure that it will be seen in the soft. I do not think that it has to be present always in the soft, because as I said, you have to take into consideration the environment, and you mentioned yourself. It is quite dense environment, can be.
But we never saw...
There's a lot of absorption.
I understand.
What's the point? That is maybe confusion? That's what you said?
That's possible. Why
Okay.
not? I don't know. I have not analyzed the data, but I know that for Batsy it's very hard. Probably it can be true, but what I really see by my eyes right now, that if I cut anything that is above zero, it means that below zero I should have Gaussian distribution, and it's definitely not so.
Well, that is good
If
point.
it's true.
I will make distribution, but I still believe that it is Gaussian.
No, I can see by eyes. That's definitely not.
So we should move on to the
Okay.
next question.
Yeah.
Why it is surprising that there was a mission before the discovery by Granite?
No, because it's...
The discovery by Granat is something random that has caused
yeah, I'm not
human
sure.
civilization.
Civilization.
Why does GLS 1915 care about the fact that it discovered it or not?
No, the cares about flux. If it's predicted that the flux is high, then why nobody saw it? That's the question. There was all sky monitors on Ginga, and there was all sky monitor on Granada. And that was operational for 2 years already at that time, or 3 years. Why have not seen it? Or why they have not seen it?
Well, we know that this was a beauty cycle, right? It's extra-transit, so there are periods of time, years when they don't show any activity.
Well, yeah, but this
It was
is...
active on this day. It could have been active a few months earlier, but the period of activity could have easily begun few months earlier. There's nothing special about the day that Granat detected it.
Yeah, yeah, I don't...
How frequently was the monitoring done? You say the all-sky monitoring.
All sky monitor of Ginga, I do not remember. I think it was looking for a pretty big part of the
Ginga was
sky.
much less
It was a
sensitive
big part of the
than
sky,
bats.
but not often.
Ginga and Granat were both much less sensitive than bats.
Yeah,
I'm not...
that's
So
true.
the fact that there were detectors and they're much less sensitive.
If I would claim it explicitly, then I would write a paper. But I'm not claiming explicitly. I just wonder why these error bars are definitely not compatible with the spread of the points. That is clearly can be seen.
We can have a look together.
Are there any more questions? Okay, well, thank you. Thank everyone in the